It's an honor to be here today talking to the OSE students and community about this project that is very new at Georgia Tech and expanding and has many opportunities for students to get involved and help us build the solutions kit. I'm going to talk about where we are right now, and I know that you will agree by the end of this that this is meeting a very clear need down on the coast for solutions around sea level rise and coastal flooding vulnerability in coastal Georgia. And you'll also see that there's a very large team of stakeholders that we are also working closely with. And it's an exciting place for students to learn how to work in translational research, where you do some fundamental work to provide new tools, new data streams, new frameworks for understanding the physics and what they mean for the coast, and to move that into a space where they're delivering concrete solutions to real people on the coast. So that's a high bar. I don't mean to say we are there yet, but we are very excited to be working towards that goal and to enacting that every time we get together as a project team to keep that challenge in our sights and to chip away at it and to learn ways to talk together and learn from each other. This is just a very collaborative space. So I wanted to call out my co-PI on this project, Russ Clark. He is a computer scientist here at Georgia Tech. He is the one who literally designed the sensor that I'm going to be talking about today from component off-the-shelf parts. It's really designed for this explicit application, and it's working really well. And we're really excited that we can combine his computer science expertise with my kind of oceanography expertise and see what we can end up with. But aside from these two people who are kind of the project leads, we have two other project leads down on the coast in the form of the director of the Office of Sustainability for Savannah, Nick Deffley, and Randall Matthews, who is a staff at the Chatham Emergency Management Agency down on the coast, worried about acute coastal hazards, including flooding. And so the four of us make up really the project team. And we take calls together, we decide everything together about this project, and we keep each other's needs and constraints on the table, no matter what we do. And so I wanted to call out those four people in particular. And I also wanted to note that aside from the four people I just mentioned, there are basically an author list of 25 people that has to go on each of our abstracts because it's really a collaborative effort across this campus and through other units at Georgia Tech, like Seismic, which is a non-academic partner to the project, consulting on the educational and curriculum development around the sensors and the data streams and the sea level rise threats. So getting into schools down there is a major goal of our project, and they're helping us formally design new curriculum for the project to go into high school and middle schools. So there's people from Seismic, there's people from civil engineering, one of whom just popped his head in here, David Frost, who's also affiliated with the Ocean Science Engineering Program, and two other PIs from civil engineering working on infrastructure. How do we represent infrastructure in the framework for coastal flooding risk and vulnerability? So as you're going to see, we're talking about some pretty high-level modeling techniques, and just having the physics isn't enough, right? And just having the land isn't enough, and just having the rain isn't enough. You need to have the infrastructure in that framework to help you decide. So civil engineers, computer scientists, earth and atmospheric scientists, county and city stakeholders down the coast, education specialists, and we have a burgeoning team of people actually interested in design and data visualization here as well from computational media. So it's totally crazy. Suffice it to say, it's a large group, and we're all very enthusiastic, and we're kind of getting towards the same results. We're only 6 months into this project. So our core problem here that we're interested in today is coastal flooding hazard and risk. And so this is just a graphic that SEMA puts together. This is out of their latest report on storm surge impacts around the Savannah area. And so you can see the categories of hurricanes that leave acute flooding across the entire county. And so obviously that gets worse as you get up to the category 4 and 5s, but even a category 1 and 2 hurricane with storm surges of no more than several feet leave much of the county already underwater. that's the nature of the flooding risk down on the coast here. And so they've had some recent brushes with Irma and Matthew on the coast in recent years that has heightened awareness around their storm surge risk. Having gotten lucky for a couple decades in a row, this is becoming a very near and present threat for them. And so we just showed up at the right time, in the right place, if you will, talking about how we could bring some sensor technology to bear on this problem and how we could serve their needs, right? So this is also an economic area for the entire state in southeastern U.S. in the form of the Port of Savannah, which sees a huge traffic and commerce and the source of many supply chains across the entire southeastern U.S., also extremely vulnerable to flooding as well. And so we are kind of thinking about the lens of vulnerability from in-town communities that are underserved, minority, majority communities, all the way up to Port of Savannah vulnerabilities and what that means for the economic well-being of the region, and of course the larger region as well for the southeastern U.S. This is the neighboring county, Glynn County, where we're also beginning to do some work. And here, this is a different map put together by their emergency managers showing the acute vulnerability to flooding down there. Looks very, very similar. The entire county is inundated at about a Category 3 hurricane. And some of these exceptional vulnerabilities are in St. Simon's Island and the barrier islands there, where they're pretty heavily populated and people have been living there for generations. And people are desperate for some solution, some way to understand and quantify what they might be facing going forward. So that's a local coastal hazard vulnerability focused on storm surge. But of course, when you talk about coastal flooding vulnerability, you're talking about recognizing a global sea level rise as a growing threat. And so this is a plot of NASA altimetry data going back to 1993. So indicating that this global sea level rise on average of 3.2 millimeters per year is not going to slow down. It's only going to get faster, of course, and accelerate going forward. How much, we don't know, but we'll talk about what the experts do say in the coming slides. But if we project this sea level rise rate out, we're about a 12 inches absolute bare minimum over the century. Fort Pulaski is the only NOAA tide gauge on the Georgia coast. And so, as you might imagine, that doesn't present a very well-rounded picture of coastal flooding hazards and risk for such an intricate set of coastlines with such a rich spectrum of vulnerability. And so this sits right at the mouth of the Savannah River, and you can see also has a long-term trend to it, in this case going back much further than 1993. On average, coastal sea level rates here are very pinned to the global average of 3.2 millimeters per year. And so this is not off from that global number I taught you about before. So it's amounted to about 10 inches over the last 85 years of this instrumental data. If we want to go forward and look at what the vulnerability is going forward, we're folding in a lot of additional uncertainties that make it extremely hard to provide frankly, an accurate number to these communities for what they should prepare for. There's just a spectrum of possibilities that acknowledges some of the most profound uncertainties that we have in earth science around global climate change are related to sea level rise, right? Some potentially large nonlinearities in the system really come into play here, and there's just no way to get around that fact. And so what we're looking at in the rainbow of scenarios here up to 2100 are the low-end scenarios where we're following very low emissions growth over the course of the century, hewing to agreements like Paris and the next phase of Paris and the next phase of Paris that will let us be fairly aggressive to keep emissions down, all the way up to some of those higher emission scenarios in the warmer colors, and folding in additional uncertainties to an extreme scenario at the 2100 mark that is 2.5 meters over that time frame. So those are very different worlds for coastal Georgia, right? Half a meter is profoundly different than 2.5 meters. And so when you go down the coast and you show people this plot, people just kind of go white in the face. How are you supposed to approach this as a community? How are you supposed to prepare your community? What kind of decisions do you need to make as investors, as homeowners, as residents, as mayors, as emergency planners and responders. So this is a very, very tough place to be in. If we want to look at for how that comes down to Fort Pulaski, this is from the National Climate Assessment. I refer all of you to this amazing document that contains a wealth of kind of global scale overviews, as well as some hyperlocal depictions of climate change impacts, this being one of them, a coastal sea level rise projections for Fort Pulaski, and really contains also a huge amount of information about economic risks to from climate change, indigenous risks, all of the different things that we might want to understand about the United States vulnerability to climate change. And so this is the Fort Pulaski. You can see that what has been a rising vulnerability to flooding becoming more frequent is obviously going to accelerate going forward quite dramatically. And so those high-end projections are in the tens of inches and several meter range. And so this is obviously one of many kind of potential impacts from climate change. We hear kind of every week, we hear about a new iceberg breaking off Antarctica, size of Rhode Island or Connecticut or some other state. Sounds very large. This is happening. Questions about tipping points, some signs of acceleration in ocean heat content that had heretofore been undetected, now emerging from better data sets, better analysis of those data sets. And so the faster and the farther we go down these current emissions trajectories, the more we should expect acceleration in the response to these, to the forcing. And the more we approach that famous catchphrase up there, this idea that there's a tipping point out there beyond which we could see a kind of cascade of accelerating climate impacts that our models just are not equipped to capture because of their intrinsic limitations. So, but here and now, we have already the emergence of episodic flooding, nuisance flooding, blue sky flooding down on the coast of Georgia. So this is a high tide, a picture from high tide taken over Thanksgiving weekend last fall, where it wasn't that there was a hurricane coming through. This was a particularly strong wind event from the northeasterly direction that piled up water in very specific areas of Chatham County and left others dry. This is because of the confluence of wind forcing and the intricacy of that coastline. And so this flooding is no longer a thing of the future that might. This is a kind of a day-to-day issue for coastal residents, right? And the predictability of where the water is going to go is very poor. Even if you know the wind event is coming, it really depends on the direction, the speed of that event, how it interacts with the tides, to know how vulnerable specific packages of communities are going to be. And this is now, let alone in 10 years and 20 years, let alone a storm that's coming through, let alone an extreme precipitation event that dumps, tens of inches of water over several days, let alone all those other additional threats that can start to compound in this community. And so what we need to do is we need to understand how to deliver real-time information to stakeholders and decision makers such that before they get into an emergency scenario, they can begin to understand and predict some of the vulnerabilities that they might expect. If you have a Hurricane Florence coming across the ocean at you, you have some formal storm surge models put forward by NOAA, of course. And then if you want to do a layer better, you're going to want to know how that wind interacts with the coastline in your community, how those rainfall projections may run off and pile up and compound your threats and risks. So this is a long-term challenge, obviously, to provide some kind of forecasting ability. Then during the event, you need to be monitoring in real time the vulnerability of critical infrastructure, right? So you want to know when a bridge is starting to go underwater. You want to know when a substation is inches from being thresholded. You want to know when a causeway is coming with inches of flooding, because as good as our forecasts are, the real-time information is really what you're going to use to make decisions on the fly about resource allocations and where to deploy limited resources to keep people alive and keep property as safe as possible and to keep your system from failing in critical places. And so after, it's also important because after the event, you need to basically resurvey some of that critical infrastructure to ensure that it's still safe structurally. So it's not enough to know that it went underwater and it's like open for business. That's not how it works. You actually need to go survey the bridges that were touched with salt water during an event like this and give them a structural survey, and then you open them for business. So what happened after Irma was, when faced with the hundreds of bridges in Chatham County with no information about where saltwater touched, they basically had to survey most of those bridges, right? And so when we went to them and we said, we have this idea for some sensors. We don't know how you would use them. We have ideas. They said, put them on bridges so we know if saltwater touched that bridge during an event. Then we can open back up faster after these events. That's what the number one thing they said to us. So that's where we're putting the sensors right now. This brings us to our project, Sea Level Sensors, Smart Sea Level Sensors, and the website, sealevelsensors.org. And here you can see some of the names of some of the leads that have been instrumental in getting us to this point. On the Georgia Tech side, you see Monty DiLorenzo and David Frost, who are involved with OSE, as well as computer scientists and these folks from GT Savannah and Seismic, who have been able to, again, help us with the curriculum development, and the city and county leads on the project as well. So you can go to the website and check it out. It really is quite comprehensive and allows you to dig in a little deeper. But the project goals are really focused first and foremost on emergency planning and response, because that is the application that we're targeting. That's what our stakeholders need the most. When I spoke to the mayor of Savannah and I said, here's the sensor, what do you want? He said, emergency planning and response, capacity building, obviously. This keeps people safe and their economy as little damage as possible. And so for this, we're really looking at these data streams providing portals for accessing real-time information by stakeholders that could be members of the public for a lesser product, as well as really enhanced portals that overlay critical infrastructure that allow decision makers to really try to see in real time what the vulnerabilities are and deploy resources in real time. So those are ongoing kind of portal and toolkit developments. And then we're really looking at more broadly mapping out and quantifying short and long-term risk to the community from coastal flooding. So it's one thing to think about a hurricane landfall. That's one set of decisions, but there's a whole other set of decisions around how you prepare your community for chronic and ongoing and increasing vulnerability from sea level rise. Those are two separate buckets. We want to contain our project around both of those goals and think about what we can do to add capacity to those assessments. Very much needed by the county and city stakeholders down there. Really, really needed. And then we have this educational component I mentioned before, where we're in schools, in middle schools and high schools down there. If our curricula are successful, if people like them, they can be propagated across the coast. Right now, there's no sea level curriculum across all of these schools on the coast. And these are communities that are going to be grappling with this set of challenges, caught between a rock and a hard place for the next decades. And the school children have no formal training in what sea level rise is, or what the nature of coastal flood are, and how the community can keep you safe during a coastal flooding emergency, right? How to keep yourself safe during a coastal flooding emergency. So this is some of the things we hope to bring to bear. And then, of course, this communication and building awareness, not just amongst the school children, but across the broader community there. Very eager to partner with the emergency planners, whose job it is to do that, and to try to see how we could leverage our project and different kinds of audiences to engage with on the awareness building, because this is essential for these communities. And I'll talk just briefly about that. So right now we have, that's a little outdated, we have 12 sensors in the water right now, and this is a very dense network compared to, like, we think about the tide gauge network that we use for monitoring global sea level rise. We have one across the whole coast of Georgia for that purpose, but these are often only kilometers apart, if that. And so our goal is to build out to a network of 50 by the summer. And so we have 30 in production right now. We finished designing our sensor in December. So we're really doing pretty well here in terms of an early build out. And the technology works as follows. You can see the sensor here mounted to a bridge, and it has an ultrasonic sensor coming out of the box, and it has a obviously a board that manages the guts of the electronics in terms of pinging and relaying that data back to a gateway that archives that data in a data server here at Georgia Tech. And so the beauty of this system is it's very, very cheap, and it's fairly accurate, and it's based on technology that doesn't use cellular data or Wi-Fi technology. It's based on the LoRaWAN communication protocol. And so right now we're measuring water level. So right now we're only looking at the ocean, but we hope to deploy sensors in inland environments where we know are vulnerable to chronic flooding from freshwater inundation or extreme precipitation events. So we can monitor that as well. That will be essential in terms of getting a full risk assessment for something like a hurricane, where you have high winds and storm surge and precipitation. Do you have a question? Okay. And then we are currently measuring air temperature in our sensors as well, which is relevant to heat stress. For example, during Savannah summers, there's some vulnerability there, and that will grow with climate change as well. And planned, we are developing, together with some folks at Skidaway, some sensors that could incorporate ocean properties into them. So obviously we're thinking first and foremost ocean temperature, that's easy. Harder is salinity, harder is pH, harder is nutrients, but we're really interested in developing some, in deploying some sensors for that. Air quality is a huge request from the community, right? When we say, what would you like to know more than like water level? The first thing they say is air quality. Can you get an air quality sensor on this backbone to help us monitor in real-time air quality? They have huge issues with that, especially across underserved communities and acute asthma rates amongst children. So they want that. We're going to try to deliver that. And as I mentioned before, the inland flooding piece. And so the gateway device is fairly inexpensive. It's $1,500. It can service thousands of sensors if it wants to, depending on the data streams and the volumes of data coming through, obviously. They have a 1 to 4 mile range at the coast. Maybe that's going to be a little bit less if you're in a densely forested region with big infrastructure, a little bit more if you're in more open ocean environments. And that's super great. And then we use that to plumb into city and county facilities that have backup power and internet. So in the event of emergency, the idea is our network can stay fully functional. That's the idea. So this is the backbone that we call the Internet of Things backbone across this sensor network. And so we can deploy basically all kinds of different sensors that will use this gateway technology to relay information back in real time, whatever parameters we would like to. And so this is, we hope, we are testing this right now, but we think it's going to be fairly accurate. There's no reason why it can't report back to something like a millimeter, maybe 5. Obviously, the surface of the ocean isn't just static, so there's a lot of noise and post-processing that we're working on right now in terms of what do we offer up into a data portal that's useful, and what do we want to make sure we deliver data that's appropriately has uncertainty bars and is processed that to be useful and meaningful and not spurious. The battery life is long enough that the city and county that's deploying this infrastructure doesn't have to service it every 6 months. That's a huge cost. And so the service schedule is not onerous for communities that are cash strapped and resource strapped. And the sensor itself is very inexpensive. We're building them now for under $300 a pop. So that's pretty good. That means that we can get these things out into the environment with very little money, compared to something like a NOAA tide gauge, right, which is tens of thousands of dollars. So that's where the benefit is. I hesitate to present Manu's work in front of Manu. This feels a little strange. So Manu, I don't know if you want to chime in here. I'll just go. I'll just be the coastal ocean modeler for a minute. But this is the modeling aspect of the project that is wedded to the project goals and deliverables. Yeah.
Right. Kunjamin is actually the student who's doing this work.
Kunjamin. We are so happy to have you on the project team. And you should come down to Savannah one of these days. You should get your advisor to shell out for a nice trip to the coast. I don't know why you can't come to our project meetings down there. They happen, we have the next one March 27th. Anybody's welcome, it's open, but you should especially welcome. Okay. So this is a coastal ocean modeling framework that was developed in collaboration with Nadia Pinardi at the University of Bologna and her group. And so we have this very close collaboration with them. You know them very well, Gian Giacomo. and the CMCC group in general, hugely helpful in making sure that we have something to work with, that the students can help evolve and help understand its fit for purpose and how it can be used as a research tool more broadly, and specifically how it can serve our project goals. So this is work that's still ongoing. And the grid goes from the open ocean down to the urban scale, really like the meter level scale here. And it has this adaptive grid that can, as you can see, thread into these tributaries and allow us to, move water and its properties around and track temperature and salinity right now, water level. Eventually, we could get more fancy. But the first steps we want to take are really to make sure that this model is running smoothly. And in particular, right now, we're trying to incorporate some of these major rivers and make sure that we have those in the model. That's kind of harder than you would think. But eventually, what we'd like to do is use it as a test bed to try to map some of the coastal flooding risk space. Nature only delivers us so many opportunities to learn from extreme events, right? We want to learn before they happen, thank you very much, if we possibly can. And so we can blow winds over this model, and we can blow hurricanes through. Eventually want to get to the point where we can not just have a coastal ocean model, we can actually plummet to a hydrology model, and we can rain on the domain, on the land bits of the domain, and we can watch water run into the ocean, right, across our community, and contribute or dissipate flooding, as the case may be. And so this requires a kind of a fully integrated land model. And if we get to the infrastructure piece I mentioned before, we have the civil engineers who are experts in modeling infrastructure and incorporating infrastructure into such systems. And so we're hopeful that kind of in this order, if you will, we're going to be marching forward to make this model more comprehensive, a better fit for purpose, and something that would be, I think, a very valuable research tool for not just our project, but for many other projects. Do you have a question? Are you just excited? I love it. I love it. Okay. So this is the initial simulation that they did. This is now several months old, but it's basically showing you that the water is coming up and down with tides, perhaps very relatively boring, but obviously the tidal signal is the biggest signal that we have on the coast. And frankly, it's the one that we're most interested in capturing in the sensor network as a first pass, because it happens so often. And we do have anomalous tides quite frequently. They're not like huge flooding catastrophes, but we have a rich history of tides coming into our sensor network. And so the first step is to try to reproduce these tides and benchmark them. And so here's an example of the Fort Pulaski sea level record over the last, this is a snapshot from January of this year, where the model is trying to reproduce the observations. You can see in general it does pretty well. That's because it kind of does tides kind of at the right time. But you can also see some amplitude modulations in the observations that we may not have in this very idealized model that doesn't actually fully incorporate yet any of the forcings or some of the intricacies we may need to think about in nailing something like this. But it's not just Fort Pulaski, it's actually the whole data streams from all the sensors that are really going to help us accelerate our understanding in how to understand. And eventually, when we understand, we can forecast and we can predict with better confidence. That's why this stuff is so important. So moving on to the educational piece just quickly here, I wanted to mention that we're super excited to partner with Jenkins High School. It's a public school down the coast. They have an engineering program, one of the top engineering programs in the state, from my understanding. And they have these two amazing teachers down there who invited us in to visit their students and talk about how they could use the sensor program to basically allow the students to get their hands on some equipment and understand these data streams and what they mean for residents. And so these are the two teachers here. This is Tim and Jama, who have been the leads on their curriculum development. And as of January, we delivered all the component parts of the sensors to Jenkins High School. And they are writing their own manuals for how to assemble these sensors. It's like super cool stuff. And so we're like, oh, you're going to write the manual for our sensor assembly. And then the idea is that this could provide a foundation for other schools to adapt this framework for constructing a sensor, modifying designs where they can, really tweaking something that's going to go in their backyard, literally go in their backyard, and they can see the data stream from the sensor that they installed. So I think it's really a holistic and compelling package for engaging students in the project that really delivers value both ways, right? Both of us. And this is an exciting event that we just did on the coast, organized by some residents in Brunswick, some concerned citizens in Brunswick, Georgia, in Glynn County, just the next county over. And this was an event where Russ and I presented where we are with the Sea Level Sensor Project. This is Jill Gamble from UGA, who's been working a lot on coastal resilience and resilience planning, basically, and flood mitigation on a community-by-community basis, and so that's her expertise with Georgia Sea Grant UGA. And Jennifer Klein works for Coastal DNR. She's also become an extremely important partner for the project. And these are some bankers and some sewage people and other people down there from the community participating in the conversation about preparing the community for these threats coming down the road. Very rich conversation. I just loved it. It's absolutely amazing. And aside from this community event, we've had very rich and deep conversations with these other key stakeholders across the coast. People like the Savannah College of Art and Design wanting to help us bring to life the sensor data and help visualize it and package it in a compelling way for public display, which is cool. All the way down to the Tybee Island Marine Science Center. They have a new museum. They have a proposal of ours. They're considering to have a whole display on the Sea Level Sensor Network. Again, I think this really indicates the appetite for this kind of work down on the coast. So it's not that we're so great, it's that the appetite is so strong that anytime you say, I want to help you, and I have a piece of technology that might allow us to learn more, then they say, thank you, yes, more, please. So that, I can't tell you in science, that doesn't really happen that way, right? We sit in our labs and we generate stuff, we publish papers, but when you're out there really working with people and trying to help them, and they're so grateful and engaged and they want to help you, it's just this magic thing that I don't think I've ever felt anything like that before in my work. So to all you students out there, don't be me. Think about doing some of this work before you get to be 45 and think about what lessons you can learn for your own work in this kind of effort as well. We both learn. They learn, we learn. They gain, we gain. And so I just wanted to mention briefly, I know I sent out this paper by Derek Loftus. He is at the Virginia Institute of Marine Sciences. And I wanted to show just a couple slides from his project. I just found this like 3 days ago. So this is a sensor network that's as dense as ours. They're a year ahead, at least a year ahead of us. And they've been deploying this around Hampton Roads, Virginia Beach, and Norfolk up there with some money from a whole different host of folks up there. So you can see these sensors, quite densely arrayed. Now, not all of these are water level sensors. Some of them are USGS sensors. So I think he has a total of 36 water level sensors deployed today, and with plans to grow that a little bit more. But I wanted to give you a glimpse of what people who are a year ahead of us have been able to do, and also to drill home the point that these kinds of sensor networks are cropping up everywhere in wealthy countries and wealthy communities. Let's be very real about that, right? But they're cropping up because people realize they need this kind of hyper-localized data and hyper-localized forecasts to be of highest use. And so really, these are cropping up and they're not even connecting to each other yet. We're all just finding each other willy-nilly. That's how fast this space is accelerating right now on the heels of some really damaging hurricane seasons, frankly. So stay tuned as we try to build bridges and accelerate learning and accelerate capacity across this network across the East Coast. But this is a project that I sent the papers out, so I would refer you to that. But they've gone so far as to have inland sensor networks and coastal sensor networks. So half of their sensors are inland, half of them are coastal. They have a full hydrodynamic model that incorporates rainfall, storm surge, and a coastal ocean model that runs to 1 meter down to at the finest level. And they are in the business of, it's kind of a hybrid data assimilation approach, but they are basically taking all their sensor data and generating forecasts on their Tide Watch website. So I would point you to that. That's how far ahead they are. They have a full website with assimilated forecasts from their networks going on all the time in real time. And so, oh, this is not what I wanted to do. So this is basically one of their stakeholder groups, and they've been working with deeply with stakeholders across the Virginia Beach and Norfolk area for about 2 years now. And they have whole counties and cities engaged with them, planning commissions. They have funding from the state that's been pretty sustained and robust. And so it kind of gives me a vision for what we could be when we grow up. Right now, our project is just still growing, and it doesn't show any signs of kind of reaching any kind of reasonable scope. But it's very, very clear that we have a lot to learn from each other as we cue the same pathways, right? I started in the same place, and I basically at 6 months, I'm where they were at 6 months. So we've all kind of ended up in converging on the same kind of framework and plan. So I think I'll end there and take your questions. And thank you so much for your time and attention.